In the last video, we decided to use the finite difference method to solve boundary value problems. So in this video segment, I'm going to present an overview of the method, and then slowly we will get into some specific examples so that the ideas can be fixed properly. The idea behind the application of finite difference method to solving boundary value problems is really very simple. You take the ODEs and the boundary conditions, and wherever you see first order derivatives or second order derivatives, what you do is you replace them by their finite difference approximation. You can use either the forward difference approximation or the backward difference approximation or the central difference approximation. We will look at the ideas related to that in a minute or so. But basically replace the first derivatives and the second derivatives wherever you see them by a suitable finite difference approximation. Then what happens because of this is that if the ODEs and boundary conditions are all linear, this idea of replacing the derivatives by their finite difference approximation will lead to a system of linear algebraic equations, which you can solve using techniques such as LU decomposition, MATLAB's backslash command, or using the INV command in MATLAB, or by using a method like Gauss-Seidel scheme. We have looked at all that. We know how to solve a system of linear algebraic equations. Now, if the ODEs and or the boundary conditions are nonlinear, then replacing the derivatives by the finite difference approximations would result in a system of nonlinear algebraic equations. And we know how to solve system of nonlinear algebraic equations because we have studied Newton method already. So whichever way, whether it is linear or nonlinear, we know how to get the solution. Therefore, we can solve boundary value problems very easily and effectively using this idea. As a first step, we break the solution domain or the independent variable domain into equal size subdomains because that keeps things simple. So we will employ equidistant grid points. For example, if the left boundary is at psi is equal to 0 and if the right boundary is psi is equal to 1. Just as an example, what I will do is I will break this distance between psi is equal to 0 to psi is equal to 1 into n equal subdomains. So the first subdomain is the distance between psi 1 and psi 2. So this part is one of the subdomains. The second subdomain is the region between psi 2 and psi 3. So this is the second subdomain. This is the first subdomain. And this would be the third subdomain between psi 3 and psi 4. And between psi n and psi n plus 1, this will be the nth subdomain. So the overall domain from psi is equal to 0 to psi is equal to 1, we will break it up into n segments or n equal subdomains. And the width of each subdomain is h, which we used to call it as the step size. Now in this configuration, as you can see, you will have n minus 1 internal grid points and 2 boundary grid points. So psi 1 and psi n plus 1 are called boundary grid points because they are located at the boundary. Psi 1 is located at the left boundary and psi n plus 1 is located at the right boundary. Psi 2 to psi n, these n minus 1 locations are called the internal grid points because they are internal to the domain. So we have a total of n plus 1 grid points. N minus 1 internal grid points and 2 boundary grid points, making a total of n plus 1 grid points. And the grid size is 1 by n. So grid size is denoted by the symbol h, and as you can see for this particular problem it is 1 by n. Of course, if the right boundary is psi is equal to 10, then the grid size will be 10 by n. So I hope you understand that. Now as step 2, you replace the derivatives in the ordinary differential equations and the boundary conditions by appropriate finite difference approximations. When we say appropriate, for some grid points, you can use either the forward or central or backward difference approximations. Typically, this will be true for the internal grid points. But for the boundary grid points, you will have to use either the forward or the backward difference approximations. For example, for this grid point, you cannot use backward difference approximation because there is nothing to the left of it. Likewise, for this boundary grid point on the right hand side, you cannot use forward difference approximation because there is no domain to the right of it or in the forward direction from psi n plus 1. So for psi 1, you may only have to use forward difference approximation. For psi n plus 1, you may have to use only backward difference approximation. For the internal grid points, you can use any of them, forward, backward, or central, but the number of points is something that you should be careful about. For example, for side 2, I cannot use a 5-point central difference approximation. But somewhere in the center of this domain, let's say somewhere here, I can use a 5-point central difference approximation. So this is what we mean by saying use appropriate finite difference approximations. A more important thing is when we replace the derivatives, either the first derivative or the second derivative, by a suitable finite difference approximation, we have to make sure that the truncation error of all the approximations are of the same order. Please note that different approximations have different truncation errors. For example, if I choose to replace dy by dx by a 2-point forward difference approximation or by a 2-point backward difference approximation, the truncation error is of the order of h. If I use central difference approximation, again a 2-point central difference approximation for dy by dx, I will get a truncation error of the order of h squared. Please note that for 3-point forward and backward difference approximation, the truncation error for dy by dx is of the order of h squared. For the second derivative, the central difference approximation, which is based on 3 points, has a truncation error of the order of h squared. So if I had a problem where I have a second derivative term and I decide to use the central difference approximation, which has a truncation error of the order of h squared, for the first derivative term in that ODE, I have to use one of these three because they all have the truncation error of the order of h squared. I should not be using this approximation for the second derivative, which has a truncation error of the order of h squared, and for the first derivatives use one of these because there will be a mismatch in the order of truncation error because these two approximations have a truncation error of the order of h only, which does not go well with order of h squared. We do this in order to prevent numerical artifacts from destroying the validity of the solution. We want all the derivatives to be replaced by finite difference approximations that have the same truncation error. So once you do that, you can set up the algebraic equation system and solve it. Again, I want to reiterate that if the replacement of derivatives by finite difference approximation results in a nonlinear system of algebraic equations, we have to use the Newton method. If it results in a linear system of algebraic equations, you can use LU decomposition or Gauss-Seidel or other methods such as the backslash operator available in MATLAB. Just want to point out a couple of things before I close this video. One, our ordinary differential equations that comes out of mass, energy, and momentum balances tend to be nonlinear in nature. Therefore, when we replace the derivatives by their finite difference approximations, we will get a system of nonlinear algebraic equations. Therefore, we must have Newton method ready to solve it. So the Newton scheme is very, very important. The second thing that you may have noticed is that I don't talk about higher order derivatives like d3y by dt cube or d3y by dx cube, etc. Because in chemical engineering systems, we do not encounter derivatives of order more than 2. Therefore, we need not bother about the third derivative or the fourth derivative, etc. I'll end this video here and catch up with you in the next video. Thank you for your time.